Good evening. Can you hear me?
Yes, sir.
Yes, sir. Good
Yeah.
evening.
Good evening. So I hope you have been waiting for only a few minutes, right? So no one joined at 8 o'clock, I hope. Because the session was changed, so I hope you know that. Okay. So we just do a quick recap of what we studied yesterday. So what did we do yesterday? So we started off with dimensionality reduction, right? So what the basic idea is that the features that are used to represent data points, right? So there, let's say there are 10 features and you have 100 data points. So all the 10 features may not be required to represent each point. So there could be some redundancy among the features, and you could represent the same point with fewer number of features, right? So that's the whole idea of dimensionality reduction. Can you represent the data using fewer coordinates or fewer number of features? So we looked at one motivating example, which is particle motion in 2D space or 3D space, right? So you can see that the particle is really moving along a line, but then uh, it's being described using two coordinates or three if you include time. So you can actually get rid of one of them. If you know that the vector here is, let's say, 1 comma 1, then all that you need is the length of the data points on this vector or the amount by which it has to be scaled. Okay, so that's the basic idea. And we looked at how this is connected to images are also data sets, right? So it's a collection of data points. So image is also you can think of that as a collection of data points. So that is something we did. And then we looked at this question of noise that is present in the data. So you can't exactly find the line passing through 4 points in this case, because a line can't pass through these 4 points, right? You can only look at, or you can only ask or search for an approximate line. Okay, and of these two lines, we noticed that this line is kind of better intuitively because it's closer to the points. So what does closeness mean? So we said that each true data point can be represented using some other point on the line, and we call that point the representative, or you can also call it a proxy for this point, blue point. So this is nothing but the projection, right? So the projection of the blue point on the line is the stand-in for the original data point, right? So that's where we get the idea of reconstructing a data set. So if you have the original data set consisting of blue points, you can project them onto this line, okay, and you can think about this reconstructed data set, which you can describe just by knowing the vector passing through this line and the magnitude by which they have to be scaled, right? So that's all you need. Now the question therefore becomes, how do you find this line? So this line is described using a unit vector w. So you start with some random w, you don't know what this w should be, and you project a point onto the line, right? So that's where we start. So this is the projection matrix. So since it's a unit vector, this w transpose w is 1. Okay, so then you project the point and you notice that the projection takes on a very nice formula, x transpose w w. Okay, so this is the projection, and then what we say is there is some error in projection. So that error is nothing but x minus x transpose w w, and we look at the magnitude of the error. So that's norm of this vector, and then since working with norms is not very convenient, you square the norm. So, and we call this the reconstruction error associated with one data point. And since there are n data points, you take the average of the sum of the, or rather the average of the sum of the squared error. So that's what we call the reconstruction error. So that is L of W, right? So in this context, W is taken as the variable. It's a d-dimensional vector as the variable. X1 to xn, the data set is given to us. Therefore, it is treated as something that's fixed or a constant. Okay. So that is where we were. So we wanted to minimize the reconstruction error, and then we did some algebra. So what you do is you expand the reconstruction error for one data point, you move things around, and you end up with this formula, which is norm x square minus x transpose w whole square. So that is the reconstruction error for one data point. Now, since the loss function only depends on w and not on the, the optimum value of W is dependent only on terms which involve W, right? So you can get rid of these xi squares and you end up with an expression like this, which you want to minimize, okay? So this is the same as maximizing the negative of this, and we ended up with this expression. So once again, we did some algebra and rephrased this as maximize W transpose CW, where C is what we call the covariance matrix, the sample the sample covariance matrix associated with the data set. So that is where we stopped. Okay, and then we briefly discussed about what is the covariance matrix. So the covariance matrix is something that measures how two features vary together. So the diagonal elements measure the variance because I equal to j, right? So it's you are measuring how xi varies with xi itself. So that's the variance. Off diagonal elements measure the covariance. So if xi increases, does xj also increase? So that is positively correlated features. If xi increases and xj decreases, they are negatively correlated, right? So we also saw some examples, and that is where we stopped. Okay, so I hope this is clear to you now. This is a very quick recap of what happened yesterday. Okay, so now where are we? So we are just for reference. So we now need to look at the following optimization problem, right? So optimization problem, what is it? So you are given the covariance matrix of the data set, which is C, and you have to maximize W transpose CW. Okay, so it's important to note that this is, we have not mentioned this, but the norm of W is 1. So we are only looking for unit norm vectors, right? So that is, I hope that is clear to you. The line is described by a unit norm vector. So it is sufficient if it is unit norm. It need not have some other arbitrary norm. So this is a way of just describing this line passing through the origin. Okay, so where is that line? So this line, right? So you can describe this line using a unit vector. So every line can be described using one such unit vector. So that's why we are just sticking to unit vectors and not any random vector. Okay, is this clear so far? The recap. Can we proceed from here? Okay, so now let's look at this data set in slightly more detail. So let's look at the data set, which is what d equal to n points are there, right? So it could be 100 points in R10, let's say. So, and the relationship with the covariance matrix. So the convention we are going to follow is the following. What we can do is we can add the data points. When I say data point, each one is a data point, x1, x2, they're all data points. So we can add the data points to a matrix, okay, called the data matrix. So we discussed this yesterday. It's called the data matrix or sometimes the design matrix. So what are we doing? So we are adding x1 here as the first column. Okay, so this is the first column. And x2 here, x3 second column, x3 third column, so on till xn. Okay, so now the shape of the shape of x is d cross n. So why is this d cross n? Each column of x contains one data point. So therefore, every column will have d entries, right? And there are n columns corresponding to the n data points, right? So some textbooks, what they'll do is, so I'll also add this as a remark. So some textbooks follow the convention n cross d. So that would mean that every row is a data point, okay, and there are n rows. So that is equally valid. So in such a case, every row is a data point. Okay, so that is what we need. That's what we'll start with. For example, right? If this is not very clear to you, we could have a data set of the form, say with having five data points, right? 5 points in the set, and first point would be say 1, 2, say -1, -3, 0, 1, 1, T. Okay, we have to be a bit careful. So all through our discussion, what we are going to work with is we are only going to work with data sets that have. So do you remember what I said yesterday? We are going to work with data sets that have something specific.
Mean as 0.
Yeah,
Mean
mean
set.
0. Yeah, exactly. Right. So mean 0. So this is a convention once again. I'll show you what happens if it is not 0 later on. But let's take this example, right? So here, what should be these two entries so that the mean is 0?
-1, -2.
-1 and
-2.
-2 or -3?
-3 because 0, 1 is there.
-3.
Yeah, -3, right? So this is an example of so yeah. So this is so x in this case is a data set that has 5 points in R2. Okay, so if you actually visualize this, it'll you can visualize this. It's not too hard to see this. So you can actually plot the individual points. So let's very quickly do that. So these are points and vectors are kind of the same thing. So 1, 2, -1, -3. So this is 1, 2, -1, -3. What is 0, 1, 1, 3, 0, 1. So 0, 1, 1, 3, -1, -3. Okay, interestingly, it is come out kind of this way, right? So these are the 5 points. This will be your data set. And what you are trying to do is you are trying to find a line. That's your goal, right? That's what you're working. So the line has to be centered here. Okay, and let's also draw a circle so that you know what we are. So the circle is nothing but circle is not needed, but we are looking for unit vectors, right? So that's why I'm drawing the circle. This is like a dotted circle. So and we are looking for vectors, right? So unit vectors that lie on this circle, correct? So that's unit norm. So what are we doing? So we are looking at directions. So it could be this direction, it could be this direction. So when I say this direction, I also mean the line passing through this, right? So that is where you're going to project it. So for example, if you're currently considering this direction, then all your x transpose W would be nothing but projections of these points onto this line. So are you able to visualize that? So it will be like this. This is your point there, okay? And its projection will be perpendicular to this line. So, and this distance is what we are cumulatively, that square of the distance is what we are minimizing, right? So it could be, so you have another distance here, and you have third point here. Okay, this distance you'll try to minimize. Okay, so if you think of these as strings that are attached to the line, as you rotate the vector, can you visualize the strings changing their lengths? So it will shrink, some of them will shrink, some of them will become elongated. Okay, so I hope you're able to visualize that part. So what you're trying to find is that orientation where the lengths of the strings are cumulatively as small as possible, right? Squared sum of the squares of the lengths of these strings should be as small as possible. Okay, so yeah, any questions so far? Clear, right? So we'll move on then. Now, where were we? So we were looking at X data matrix. So what is the relationship between C and X? That is what we have to know. So what is the between the covariance matrix and the data matrix, right? So that is what we have to discover now. So what is C? What was the formula for C? 1 by n into, what did we say? Do you remember the formula for C?
Summation xi transpose.
Yeah, summation xi transpose, right? So this is what for all the n data points, xi xi transpose, right? So if you stare at this for a while, what is, if you expand this summation, this is nothing but 1 by n x1 transpose dot plus xn transpose, right? So this is actually the same as 1 by n. You see what has to come here for, if I want to use the capital X, the matrix, data matrix X, what should I substitute here? Does anyone see the relationship?
X into X transpose.
Exactly. Yeah, that's good. So X into X transpose. Okay. So if you go back to X, this is X, right? So what is X into X transpose? So notice that X into X transpose is nothing but this is X. Okay. And X transpose will be
D cross D matrix.
yeah, so the same thing, but then all of this will become the rows, right? So this will be x1 transpose, and then many dots xn transpose. So if you recall, very early on in this course, we looked at a certain way of multiplying two matrices. Okay, so this is one way of multiplying a matrix. So you multiply this row, this column vector with that row vector. So x1 you multiply with x1 transpose, x2 you multiply with x2 transpose, xn you multiply with xn transpose, right? So this is
So
you must
is this giving length between?
length
What
of
is it giving exactly? Sir?
which one
I mean x1 transpose.
is a matrix. So we studied this, right? Very first few weeks, week 3, I think, week 2, once, and it was on a Saturday. We studied 4 ways of multiplying matrices, and this
Yeah.
was one of the ways. So it's called the outer product. So
Okay.
x into y transpose is the outer product of these two vectors, and it is a matrix of rank 1, right? So we saw this in SVD also, right? So it's last week. Singular value decomposition also does the same thing, sum of rank 1 matrices. Okay, so you can work this out. This is not too hard to prove. You can, if you stare at
No,
it.
sir, I mean, my question is like, by doing x transpose, what we are trying to do? I mean, uh, is it something related to the graph that you have shown? Like, are we
No.
trying
So
to
it
find
is.
something?
We are not trying to do anything. So this is like
Mhm.
we are connecting the covariance matrix with the data matrix. So the covariance matrix contains information about the data. So therefore, it has to be related to the data set in some way. So this is what I'm claiming is this is the relationship,
Oh, okay, got it.
right? So I'm saying that the covariance matrix is 1 by n xx transpose. So again, once again, you have to be careful about one point. So the formula C equal to 1 by n xx transpose is correct only if the mean of the columns are 0, right? So this is very important, right? That's why the convention is what we are following here. Where is it? So somewhere I mentioned, right? So the mean has to be 0. Only then this is true. If not, what you have to do is you have to see the actual formula for C is actually this, right? So 1 by n x minus e of x or x minus mu into x minus mu. This is the actual formula, right? So if you are interested in the actual formula, this is what it is. The sample covariance matrix will look like this. But then since mu is 0, it collapses to 1 by n xx transpose. Okay, so remember this. I'll box this, and we'll come back to this later. So this is 1 by n xx transpose. This is what the relationship between the data set or the data matrix X and the covariance matrix. So the covariance matrix is what is giving you all the information that you need about your data set. Okay, it's captured in this D cross D matrix. C has shape D cross D. Sorry, D cross D. In the example that we have here, the covariance matrix would have shape 2 cross 2. Okay, and it kind of condenses all the information that you need about your data set into these 4 values too. So variance sigma 1 square, sigma 2 square, covariance of x1, x2, covariance of the other one is also the covariance of x1, x2. Okay, so keep this in mind. We will come back to this very soon. So what is the problem finally that we are solving? I'll restate it. We have to maximize W transpose CW. We want to find the W which will maximize this W as unit norm. Okay. Now solving the optimization problem. That's what we'll do now. So we'll solve this. Okay. So we'll take this up. This is largely algebra here. Okay. There's not much of visualization right now. You can only do this visualization a bit later. So how do we solve this problem? So this is actually related to something called the Rayleigh quotient. Okay, you can do a Wikipedia search and you will get this. And this is related to that. So those interested can take a look at that. Now,
Sir, would you please tell us what is Rayleigh quotient?
yeah, so you can look at Wikipedia for that. So it's this is what is. That's just a simple entry on this expression that you have here. Okay, for those interested, is extra ready. So how do you maximize this? So for that we have to understand some properties of the covariance matrix, right? So what can you tell me about the covariance matrix? So first thing is C equal to 1 by n x transpose. So I have written that down. This is not really a property, but yeah, based on this, right? So having seen this expression, what all can you infer from this?
Symmetric.
Yeah, so C is symmetric. Okay, next.
Square.
Yeah, C is square. Yeah, that's why it's you can even talk about symmetric, right? So it is square symmetric. Okay. What else?
So does mean having 0 makes it symmetric?
No, it is not that. So it being symmetric has nothing to do with the mean being 0. So it is symmetric because if you do C transpose, right? So C transpose is just 1 by n XX transpose the whole transpose. You will end up getting C again. So XX transpose again.
Okay, sir.
Right?
Yeah.
So yeah, what other property does C have? This is connected to last week, so week 6. Yeah, sorry, can you repeat that?
It tells us about the variance of each variable.
Correct, yeah. It tells us about the variance of each feature and the covariance. Yes, that is true. But more from a more algebra perspective, right? So if you can think of its eigenvalues, eigenvectors, what can you conclude? So
its eigenvalue should be the.
Yeah, what is the advantage of having a symmetric matrix?
It has real eigenvalues.
Okay, it has real eigenvalues. Okay, is that the only advantage?
Its eigenvectors are orthogonal.
Diagonalizable.
Yeah. So C is symmetric. Therefore, by the spectral theorem, which we have studied, C is orthogonally diagonalizable. Okay, and also diagonalizable. Okay, not just that. There's one more property, very important property. What is the last thing that we studied after SVD in week 6?
Application of pseudo inverse kind of.
Right, but in the lectures, let's say in the prof's lectures, what was the last chapter in last week?
Sir, low rank approximation.
Yeah.
Right, that is okay. That is that.
Pseudo inverse.
Right, okay. Yeah, no, not really what I'm looking for. C is a particular kind of a matrix. What matrix is it? What? Okay, it is. I'll tell you this. So C is positive, semi-definite. Okay. So if you remember, we were actually discussing this last time, right? So this is important. Okay, why is this important? Or first of all, how do you know that something is positive semi-definite? How to test
If
for it?
its eigenvalues are
Okay, if its eigenvalues are all non-negative,
positive,
right? So
yeah,
positive,
non-negative.
non-negative. So let's look at that. Let's assume since this is anyway or diagonalizable, it will have a full set of eigenvalues. So let's say lambda comma b is a I'll use lambda I comma wi is an eigenpair. Okay, eigenvalue pair. So you know that C wi is lambda I wi, right?
Yes, sir.
So I'll just plug in 1 by n xx transpose because I know that C is 1 by n xx transpose. So this is lambda I wi. And what do you think I can do now to this equation? On both sides, I can do something. What do you think is the right thing to do? You have seen I've done this something similar a lot of times.
X transpose.
Should you multiply by x transpose or should you multiply? You should multiply by something. You want to show that lambda is positive or non-negative, right? So what will help in that in trying to show that? So maybe if I
Lambda bar.
so x, if I group this like this, are you able to see what you should do?
We have to show norm square some way.
Okay, so you have to multiply by wi transpose, right? So if I multiply by wi transpose, what do you get? You get lambda I wi transpose wi, right? So right hand side becomes just norm wi square. What does the left hand side become?
Wi transpose Wi transpose x whole square.
See, you have to be careful. This is a vector, right? X transpose wi is a
Yes, sir,
vector,
yes, sir.
right? So I can rewrite,
Wi transpose x transpose.
correct? So it is x transpose wi transpose x
Yes.
transpose wi, right? So if I do this, what does this become? Something transpose something.
X transpose W high whole square.
The norm of x transpose wi. Okay, this is the norm of x transpose wi. So this is equal to lambda I norm wi square. Okay, now can you see that lambda I has to be non-negative? There is no other go because this is positive or it can't be zero. This thing could be zero, but then still it is non-negative. So therefore lambda I is greater than or equal to 0. So that is just a quick proof that C is positive semi-definite. So the
Yes.
right, this is clear, right, to everyone? Why C is positive semi-definite? All the eigenvalues of C are non-negative. So now we come to the main part. Therefore, therefore we can express. So we can list down the D eigenvalues and eigenvectors of C as follows. So I'm going to list them in a particular order. So I'll say that lambda 1 is the biggest eigenvalue I will list it first. Then comes lambda 2, the second biggest eigenvalue, so on and so forth until I have lambda d. Okay, there are d eigenvalues, perhaps repeating that we can't say. Corresponding eigenvectors and unit norm. So I'll only use unit norm. So W1 is corresponding to lambda 1, W2 corresponding to lambda 2, so on. WD corresponding to lambda d. Okay, so now so far is this clear? So these are the eigenvectors of C, unit norm eigenvectors. These are the eigenvalues of C in decreasing order. It's clear, right?
Yes, sir.
Okay, so now what is your optimization problem? So all this we are doing so that we can solve this optimization problem. So you want to maximize this. So now I'm going to claim the following. We can also prove this, but I don't know how many of you are going to be interested in that. We have time, but I don't know. So let me just state the solution. So the solution is this. Solution, the maximum value of W transpose CW is achieved when W is equal to the eigenvector corresponding to the largest eigenvalue of C, when W equal to W1, that is. Okay. So this is the solution. So this is, can box this again. Okay. This to be an equation. W transpose CW is when W equal to W1, and W1 is called the first principal component, okay, of the data set or data matrix. You would call it either way. So what will maximize what W? We were looking for a W, right? And it turns out that the W that maximizes W transpose CW is the first principal component, what I call the first principal component, that is nothing but the eigenvector corresponding to the largest eigenvalue. Okay, is this solution clear? The statement of the solution to everyone, what we have just stated. Okay.
Yes, sir.
Okay, right. So the maximum value is achieved when W equal to W1. So how do you express this? Since optimization is also started, the formal way of expressing this is argmax. Okay, so this is the argmax norm W equal to 1. W transpose CW is called W1. So that is W1. So argmax, I hope you are all familiar. So argmax is what? Argmax returns the argument for which, or argument at which, the objective function attains its maximum, or attains its optimum, right? So we don't know if it's maximum or minimum generally. So what do I mean by this? So let's say you're trying to maximize, say x minus 1, or minimize, right? Let's take minimize. So you want to minimize f of x, where f of x is x minus 1 whole square, right? Plus 3. So what is the value of f of x at the minimum? What do you think is the minimum value of this function?
3.
3, right? So 3. So how would you express this? The minimum of f of x subject to or no constraints here, right? So it's unconstrained, is equal to 3. So this is the outcome of the optimization problem. The minimum value of f of x is 3. Okay. However, the argmin, what we'll call the argmin of f of x. What is the argmin of f of x?
1.
1. Okay. So the point at which f attains its minimum is the argmin. Okay. So likewise, the point at which W transpose CW attains its maximum is the argmax, right? That is W1. And we are going to call that the first principal component of the data set. Right. So that's the solution. Now you can, if anyone wants the proof, let me know. I will add a note here as to why we arrive at W1 and how we arrive at W1. Okay. So that's not very hard. It's quite simple. We just use some concepts from linear algebra and we can show it. Okay. So that is so far. So this completes. So this completes the reconstruction error minimization perspective. Okay. Way of understanding PCA. So PCA is principal component analysis, right? And what we have found out, so see, this is what we have found out is we have found out one principal component. Okay, so what does a principal component do? So I just want you, I want some of you to answer this. From what we have done so far, if you look at the image, yeah. So what does the principal component do? Principal component, by the way, is what is it? Is it a matrix? Is it a vector? Is it a scalar?
It is a method of dimensionality reduction such that the reconstruction error is minimized.
Correct. Such that the reconstruction error is minimized. So when I say W1 is the first principal component, I want you to tell me what is a principal component. Is it a, what object is it? Is it a vector or a matrix or a scalar?
It's a vector.
Yeah, so the principal component is a vector. Okay, so don't get confused by the names. So that these are all terminologies that you have to become familiar with. So the principal component that we see, the P and A, right, or so rather the PC, is a vector. Okay, that's the first thing. It is a vector that lives in which space? Rn or Rd or which space?
RN, RD, sorry.
Rd, right? So it's living in Rd. In this case, it's living in R2. So I have to keep copying this. Let me say so. Okay, so this. By the way, this is not the principal component. So let me draw the principal component. The principal component would look something like this. This will be the line that minimizes the reconstruction error. Okay, so it would kind of go through the data cloud, as we call it. So it need not go through the data points, but it has to certainly go through the. Okay, so that is your W1. If you try to solve this, you will get something like this. Okay, so this is your W1, the vector unit norm vector. Okay, it's a vector in Rd. So first thing you have to notice, it's a vector in Rd. So meaning it is in the same space as the data points. So here all the data points are in R2. So the principal component is also in R2. Okay, first principal component. What else can you say? Geometrically, what else can you say?
It reduces the dimension.
Uh,
If we have 2D,
okay, but even before we go there, right? So what was the way we framed the optimization problem? What did we want to like achieve? We wanted to minimize what?
Reconstruction error.
Yeah. So
Yeah,
therefore,
yeah.
yeah, always have that goal in your mind, right? So the geometry in PCA is very important. If you miss the geometry, you miss the complete picture, right? So the vector D1. So what is principal component? It's W1. We are going to call it the first principal component, okay, or PC. So that is W1, and W1 is in RD. Okay, and notice that all the data points are also in RD or R2 in this case. W1 is the vector such that if you project all the data points, in this case 4 of them are there, onto W1, the reconstruction error will be minimum. Okay, so that is the W1 that we have found out. Okay, the W1 we have found out is that vector which, if you draw perpendiculars from all these 4 data points and you calculate the reconstruction error, the squared length, sum it, that will be smallest for this W1. Okay, you can kind of see that, right? So you see how closely W1 is going through the data cloud. Okay, so is this idea clear? What is the first principal component? To
Yes.
everyone? Okay, so if you know, actually, if you want to find out, so this is the example that we have plotted, right? So let's take this. We can do it for this one example. So Let's quickly do this before we go to the other perspective. So example is this data set that we have plotted. We make it slightly better. So I can actually get rid of, I can actually plot this after doing the entire thing. So what I will do is W1 I won't have. I'll make this slightly more precise so that the individual coordinates are also visible. Let's make this 15. Let's make this blue. It's too big, right? Maybe I have to be slightly. It's too big. It's like bindi. It should not have so big. I hope this will be better. So let me make this bigger. I'm doing this because this will allow us to understand the PCs better. Okay, are all the points there? No, 1, 2 is there. -1, -3 is there. 0, 1 is there. 1, 3 is there. Oh, -1, -3 is repeated twice. It's kind of irritating, no? So what we'll do is instead of having -1, -3, let's say we have. Yeah, the problem is this should not be exactly negative. So if I make this minus, what will this become?
1.
If you want, this is 1, is it? Yeah, this is 1, and what should this become? Yeah, this is 1. Do we have 1 -3? We don't have 1 -3, but 1 -3 will kind of spoil the whole fun. Let's see. I want something that goes through. Okay, so let's work on it this way. So just give me some time. It will be useful exercise to have a proper data set to do PCA on. So let's first take all data points that are symmetric. So what will be the mean of the 4 points I have drawn?
0.
0.
Right? So what we'll do is just to add some slight variation, let us move this point up so that I don't want everything on a straight line. So let's make this 2, 3. So let's make this 2, 3. And therefore, this will become -2, mean is still 0, right?
Yes, sir.
Okay, so therefore the data matrix becomes. So the data matrix becomes 2 cross 4 matrix, which is 1, 1, 2, 3, -1, -1, and
-2, -3.
-2, -3. Okay, so this is the data matrix. Okay, so now if you are asked to do if you're asked to find the first principal component, they can also ask you to find the second principal component and so on, but we have not come across that so far. So the question could be find the first principal component. Okay, so in that case, what should you do? That's the question. Okay, so the question could be this. Alternatively, the question could be framed in this following way: find the unit norm vector. Find a unit norm, because it's not unique. Okay, find a unit norm vector passing. So find a unit norm vector such that the reconstruction error of these 4 points is minimized after projecting the data set onto this line, onto the line passing through this vector. This is too complex. You're able to understand, right? So find a unit norm vector such that after you project the data set onto this line, the reconstruction error should be minimized. Both are asking the same thing. Okay, this is like a slightly roundabout way of asking the same question. Okay, so how do you do this? So how will you solve this? So the first step is to what do you think will be the first step?
Find the covariance matrix.
Yeah, find the covariance matrix. Okay, so you have C equal to 1 by 4 in this case, right? 1 by n x transpose. So that is we write it down. So 1 by n x transpose. So maybe step 0 I would add as identify. So step 0 is identify the shapes. So you have n equal to 4, d equal to 2. So C is of shape 2 cross 2, and x anyway is given n cross, so d cross n, so it's 2 cross 4. Okay, so these are the shapes involved. So step 0, if you really want a step like that. Step 1 is find the covariance matrix, right? So this is 1 by n, so this is 1 by 4 x transpose. So let's take x here, this is x, and then x transpose, right? So what will be the shape of x transpose matrix?
4 by 2.
4 by 2, right? So this is 4 by 2. Let's see if I can paste it. Oh no, it doesn't work. Okay. So this will be 1, 2, minus 1, minus 2. So first row will become the first column, and then 1, 3, minus 1, minus 3. Is that correct? Whatever I have written.
Yes, sir.
Okay. So can you please tell me what this will be? 1. Wait, have I done some mistake? X is correct. Yeah, no, I don't think so. Yeah, it is correct. So 1 plus 4 plus 1, 5 plus 1, 6 plus 4, 10. Is that correct? Is this 10?
Yes.
Yes,
Okay.
sir.
1 plus 6 plus 1, 7, 8,
Six.
Yes.
14. Is it 14?
Yes, sir.
Okay. So this will also be 14, right? Because it's symmetric. And then this one is just norm of the square, right? So 1 plus 9 plus 1 is 10, 11 plus 9, 20. Is it 20?
Yes, sir.
Okay. So let's simplify this. You can further simplify this as I don't want fractions, but I can't help it. So 1 by 2, this is 5, 7, 7, 10. Okay. So that is your C. What will be step 2?
Find the eigenvalues and eigenvectors of C.
Okay. Correct. Find the eigenvalues and eigenvectors of C. Let's do that. So let's let you know you are experts. Must be experts by now. So C minus lambda I equal to 0. So equal to 0. So that is this case what? Half into that half goes away. So the half we can get rid of. Half we can get rid of, no? Oh, no, wait. Half we can't get rid of. So we have to be careful. So 1 by 2. So this is 5 by 2 minus lambda. And then you have 7 by 2. This is 7 by 2. And then, okay. So this is 5 minus lambda. Is that correct? C minus lambda I. 5 by 2. 5 minus lambda, 7 by 2, 7 by 2. Correct only, no? This is, can someone verify?
It's correct.
Yes.
Okay. Yeah. So then what we do, we just multiply. So 5 by 2 minus lambda and 5 minus lambda equal to, this becomes 49 by 4.
49 by 4.
Okay, 49 by 4. And this is lambda square minus, let's just put this 4 inside. Okay, so that we end up with something slightly cleaner. So if 4 goes in, 2 goes here, 2 goes there. What will it be? It will be 5 minus 2 lambda and 10 minus lambda is equal to 49. Is this correct? 5 minus 2 lambda, 10 minus 2 lambda. So it's like 4 lambda square minus 10 lambda minus 20 lambda. So that's 30 lambda plus 50 minus 49 is 1. Is this what you will end up with?
Sir, in the last second line, it should be 49 by 2.
49 by. Oh, this one is 49 by 2, is it?
Yeah.
So, oh, is it why 49 by 2?
Because you multiplied both sides with 2.
Now, okay, so I'm multiplying by 4 itself, right? So I'm multiplying this by 2 and once again this by 2.
Okay, okay. Sir.
Okay, so that's why. All right, so once you do that, you will end up with. So you end up with what? 30 square minus 16. So that's going to be some crazy roots. Can someone verify if we have done this properly?
Yes, sir, I got the same last equation.
Okay. So what will be the roots? It will be 30 square. So we should get both as positive, non-negative. That is for sure. So it is 30 plus or minus square root of 900 minus 16 by 8. Okay. So this 900 minus 16. By any chance, is it a square number?
It is 884.
Okay, is 884 square by any chance?
No, it's
If it is, life will be very easy. If not, I'll have to take some other example later. P dot QRT of 884 is what?
29.73.
Okay, so it is, yeah, 29 point something. So it is not a square, unfortunately. Okay, so it is not a square number, but you will end up with lambda 1 and lambda 2. Okay, so you have to trust me on this. So you'll get some, of course, we won't give you such bad numbers in the exam. So once you find the eigenvalues, what is remaining? Eigenvectors, right? So you have to do the usual business. So here, sort them in descending order. So that's the main thing. Sort them in descending order. Say, assume that lambda 1 is the bigger one. So lambda 1 will be greater than lambda 2. So if you final answer will be find an eigenvector corresponding to lambda 1 and normalize it. Okay, that's the final step. Is this clear? So that will be step 3. So this will be that will be step 2.1. So if you want to put it that way, find the eigenvalue. Step 3 will be, this is step 3. So find the PC, so principal component. So sort the eigenvectors in descending order, choose the largest eigenvalue. So sort the eigenvalues in descending order, choose the largest eigenvalue, find an eigenvector corresponding to it, and normalize it. So that will be your first principal component. Okay, so unfortunately I couldn't give you an example where the values turned out to be proper. So sorry about that, but yeah, maybe during the solve with us we will come up with a proper example. Okay, any questions in how to find the first principal component?
No.
Okay, great. So then we can go on and look at the second perspective. So whatever we have been doing is reconstruction error minimization. There is another concept or another way of understanding PCA, which is called variance maximization. So before we study that, I want to talk about the idea of variance, because variance is used in a very particular sense here. Okay, so look at this data you have. So I have given you a data set here. It's the measurements. It's the temperature measurement, let's say. Okay, across a given day. So different time instance in a given day. So this is the measurement that you have. Now, okay, so maybe that is temperature is perhaps not what I want. Let's say weight measurement, but let's take this for some adult. So it is like 60.1, okay, 59.9. So assume that this adult is man or woman is traveling to different places, okay, on a say 2-3 consecutive days, and wherever this person goes, what they're doing is they are measuring their weight on different weighing machines, okay, and these are the readings. So 10 different weighing machines, 10 weighing machines, so give these readings, okay. Now the weight is, strictly speaking, it can vary, but then it won't vary drastically in like single day, in across few days, right? Assuming you take the measurements on the same at the same time every day, right? So assume that you take the readings at a fixed time, say before breakfast every day. So what can you say about the variance of these measurements? Ideally,
Yes.
what would you like? What would you like variance to be? Less or more? Large or small?
Small.
Less.
Yeah, small, right? Or less, right? So this is what you would like, because your weight is, let's say, 60, and that's your mean weight. Any deviation from that, you would like it to be less. Okay, so the deviations are probably coming because of daily variations or because of faulty or faulty weighing machines, right? So there's one way of understanding the variance where it is a measure of your error, okay, so or deviation from the mean, which can be interpreted as the error. So one way to understand variance is to look at it as a measure of error, okay, in a physical measurement. So you would have all, I'm sure, you would, at some point of time, done experiments in physics at school. So you have to measure the mass of an object by dipping it, find the density of the object. So you would be asked to take 5 different measurements and find the average, right? And a good experiment is one where the deviation from the mean is not too much, right? So that your goal there is to minimize the variance. However, we see that we are talking about maximizing the variance. So what is variance really? Okay, so you have to understand it differently when it comes to data science. So look at this scenario. You are measuring the weight and height of students in a class. So you have 2 classrooms. On the left is, say, class 10C, okay, some 10C. This is, say, class 10D, okay. 2 different classrooms are
It's 10 o'clock.
present here, and these are the weights of the students and their heights, okay, of 2 different classrooms. So what can you say about the variance in the height? Variance in the height of 10C and 10D. Which is having higher variance? Okay, so 10C is having higher variance, right? Now, which one do you think is more natural, or what do you expect a real world situation to reflect?
10C.
10C, right? Now,
Yeah.
there is a way of understanding variance, okay, where you can call it the information content in a feature. And okay, so the more the variance, you could say that the greater is the information that the feature can give. Okay, so greater the variance in a feature. By the way, weight and height are features. So greater the variance in a feature, greater the discriminative power of that feature. Okay, so why does this make sense? So remember, why are we doing data science? So what is the goal? It's a very philosophical question. So goal of data science So can someone tell me what is the goal of data science? We are in this program. We have been in this program for so long. We are almost going to enter. Yeah, second.
The role of data science in real world, I think, to find the dependent variables on some means to find the variables which are dependent on some other thing. Means the
Okay.
relation data.
Can you be slightly less abstract?
So I think it is because of that we can relate the real world with data science.
Okay.
So it's like understanding the data and come up with the trends and patterns across.
Yeah, yeah, that's correct. So
Useful insights.
yeah, exactly. Insight is what I'm looking for. Of course, the other answers are not wrong. So see, the goal of data science is to extract insights from data, right? So that you can make decisions based on that. So in fact, there is a very nice way to put it. So data science is the process of converting data to decisions. Okay. So for example, here this is not a decision making problem, but it could very well turn into a decision making problem. So if you are measuring the height and weight and you say that based on this you want to take some decision, so the decision will depend on some insight that you gather from the data. Okay, so the insight here on the left hand side is that, what is the insight if you want to express it in a single sentence?
Height is made varying more than the weight.
With the increase of height, there's increase of weight.
Yeah, so as the height increases, the weight increases. Okay, that's the inference. That's what you gain. That's the insight you gain. So, and notice that because there is a lot of variance in height and weight, you are able to make that inference, right? So in this case, if you notice, the height is almost the same. It's a very peculiar classroom. Okay, you will never see classrooms like this, but still, I'm saying. So you have these many students in the class, and all of them are roughly having the same height. So there is very little insight that you can gain from the feature called height. Okay, there is no variance. There is no, only if there is some difference does this feature matter, right? So what you can do is, since all of them are having more or less the same height, in 10D you can just throw away this height feature and you won't lose anything, right? So do you get the idea? So if you, so that is why variance is important in data science, because it helps you bring in that discriminative power. So here height has a lot of discriminative power. So if I know that the height is small, I know I can say that the weight is also small. Here I can make no such claim. So height is a dummy feature here, useless feature. So the goal of so the higher variance means higher information. So that is why we are, one way to think of a data set is finding patterns in data set is find, so find directions in which the variance or the information content is maximum. Okay, so now you rephrase the whole problem in terms of variance. So look at the green points or the blue points. Now if you consider this line and the projections, then what you're saying is the spread of the data points on this line, okay, should be maximized. So choose that line which will maximize the spread. So I'll just, in parallel, I'll draw another line. So here, what is the spread? It is this distance squared plus this distance squared. So the sum of the square distances
So
of the
X is in increasing order.
yeah. So the distances of the red points from the origin should be maximized in some sense, right? So sum of the distances. So I'll show you the same data set, but then with a case where the variance is not so much. So let's make this small. Okay, let's look at some other direction. In fact, I'll show you a direction which is where the variance is going to be very small. Okay, so this, all these red points will move here. So this is the projection corresponding to this blue point. Okay, very roughly drawing. I'm not I don't have time to draw it exactly. So this is for this point. Okay. And for this point, you have, this is the projection. And for this point, you have, okay, this was for this, right? This fellow is here. So this is like project, 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 come here. So I'm hoping you will draw these vertical lines later on, dotted lines. So can you see that compared to this line, the spread of the red points is lesser here?
Yes, sir.
Yes, sir.
Okay. So the variance of the projections, okay, or that is lesser here, it is more here. So you want to look for lines which have maximum variance. Okay. So you can rephrase the search for a principal component as, you can define a alternative principal component. So alternatively, a PC could be one which maximizes the variance of the data set along the line. Along it, I would say along it, right? So, and interestingly or very surprisingly, the direction, so the main insight is that the direction which minimizes the reconstruction error, okay, is exactly the same direction which maximizes the variance. Okay, so this is the beauty of PCA. So you look at, you put two different ways of solving the problem, but both of them are actually one and the same. Okay, so is this clear, the idea, the basic intuition behind variance maximization? Okay, so now we will go and see how the math works out. The math should finally work out, right? So if not, then the claim is not at all true. So principal components, we come to that. So yeah, where are we? We are here now. The question now is, find the variance of a set of points along a line W. Okay. So first we start with one point. So if you have a point X and if you project it on the line W, X transpose W, W is this. So what is the distance of the point, red point from the origin? The squared distance of the projected point from the origin is what?
Mod X transpose W, W whole square.
Yeah, more X transpose W. So X transpose W square, right? Because if you think about it, this is the W's unit norm. So if you take this transpose this, you will end up with X transpose W whole square. Okay, so does everyone agree that this is the distance, squared distance?
Yes, sir.
Okay, so if you have n points now, the sum of squared distances is the variance of the projected points from the origin. Okay, origin is the mean, right? So variance, I don't need to call it from the origin. This is the variance of the projected points. So what is the variance? It is deviation from the mean. Recall that variance is deviation from the mean. The mean is nothing but 0, 0 here. Okay. So what does this become? Is this correct? Recall that the variance is it just the deviation from the mean or something else? Statement
So
is wrong.
mean deviation from the mean.
Okay, so it's
So
not
mean or
just
square deviations.
squared deviation, right? Yeah, it's the mean of the squared deviations from the mean. Okay, I hope you understand what we mean by that. So 1 by n, which is like the mean of, so first of all we take square distances. We just said that this is the square distance from the origin. So this is xi transpose w squared. Okay, this is x1 transpose w, right? So this is one data point square distance from its mean, right? Data sets, the projected points mean. So if you sum this up, this is the sum of the square distances, and you have to take the mean of this. Okay, so what is the mean of this? 1 by n. So this is what is the variance of the data set along the line w. Okay, we call this the variance of the data set along the line w. So this is the image that you have to keep in mind now. So it's not making sense, let me know, right? So these are like slightly hard concepts, so they may not make sense right away. So unless you tell me, I won't know. So
Sir,
yeah.
I am telling that variance will work, but if I take the ST also, standard deviation also, will this work, or is that
Standard
parameter?
deviation is a pain to deal with because you have to keep track of square root of variance. So why bring in square roots, right? So it is convenient to work with variance. Okay, so I am drawing the distances from the origin. Origin is the mean here. So I want you to tell me if you are able to understand this part. So this is the square distance. This is the final distance. So final distance will be this big. Okay, so what is this? This is like x1 transpose w. Okay, this length is x1 transpose w, and I can't do this for everything because we'll waste time. So this is like x4 transpose w. Okay, of course, absolute value. So if you want to treat this as a distance, it should be absolute value. So this you are squaring, this you are squaring, you're adding all of them, dividing by n, and this is what is the variance of the data set along w. Okay, so what is this now? You have seen this before. Have you?
C.
Is the whole thing C or?
What is inside the brackets? Xi transpose W's.
Okay, so notice this. We did this before, but I'll just do it once again. So what is variance of the data set along the line W? That is 1 by n, and so this I'm copying x1 transpose W square, blah blah blah, all that, right? So 1 second. So this is kind of stuck here. Okay, so this is what we have right now. I'm going to very quickly do this. You are going to verify this later on when you have time to revisit this. So this is xi transpose W, okay, into xi transpose W. So I can do this as xi transpose W, xi transpose W. I'm taking one term. I can swap the order because it's a scalar, right? So I can say it's W transpose xi. And then I can get rid of the brackets. So this becomes W transpose xi transpose. So what I can now do is I can take the W transpose out and okay, W out. So W transpose and W I have moved out. This is nothing but x1 transpose. This is just sum, right? So x2 transpose, so on. So in fact, this will be like dot 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 dot. This will be n. This will be n. And what you have inside is C. Okay. So this is what 1 by n. W transpose once again the covariance matrix C. Sorry, this whole thing is C. So 1 by n into this is C. So do you all get this at least somewhat? Not entirely.
Yes,
Got
sir.
it, sir.
Okay. Therefore, what we maximize. So remember, when we are minimizing the reconstruction error, the optimization problem we were solving was this maximize W transpose CW. It turns out that this is nothing but this is the same as saying maximize the direction along which the variance, okay, or find the direction along which the variance is maximized. So finally the conclusion is the direction along which the reconstruction error is minimized is the same as the direction along which the variance is maximized. And you will see that, so you will see that the variance is actually nothing but the eigenvalue of C. So for that, you need to understand W1 transpose CW1. Okay, this is the maximum value, right, of this expression. So what is CW1? W1 is
Lambda
what?
1 W1.
Yeah, lambda 1 W1, because by what we haven't shown this, but we said that argmax of this is nothing but W1, right? So the eigenvector corresponding to the largest eigenvalue, right? So this is nothing but lambda 1 W1. So now if you expand it, you will end up with lambda 1 into W1 transpose W1. But what is W1 transpose W1?
1.
1, right? So W1 is a unit norm eigenvector. That is what this means. Okay. Therefore, this is a very nice result. The value W1 transpose CW1 is nothing but the variance of the data set along the first principal component. Okay. So in general, in fact, you can show this. W transpose CW is the variance of the data set along the direction C. Sorry, along the direction W. This is the general idea, and this is if you plug in W1, you will get the variance along W1 direction, and the variance is nothing but this is nothing but the largest eigenvalue of C. Okay, so the eigenvectors and eigenvalues of the covariance matrix have a very nice interpretation. So the eigenvalues, the largest eigenvalue of the covariance matrix is the variance of the data set along the corresponding eigenvector, which is called the, what is this eigenvector called?
First principal component.
The first principal component. Okay. Yes. So component. Okay. Yeah. Okay. So that is so much for only one principal component. How much time we have? So we still have some 10 minutes more. So you can extend this idea. So this will require a lot of extra math for which we don't have time. So or it's kind of out of scope. So I'll just tell you what is there in the lectures and what you need to realize. So remember, what you have done is you have only found out one direction which is important. Okay, but there is no reason why there should be only one direction. There could be several directions. For this, you have to go back to this image here. Okay, so remember that so this is other PCs, other principal components. So remember this case, right? Your data is actually living in a two-dimensional space. So you can't explain this using just one principal component. Okay, you would need at least two. So in fact, you would need exactly two, right? So how do you find the other principal component? So whenever I say principal component, you should think of directions which maximize the variance. So there is a way to find other principal components, and I'm just going to give it to you here without proving it. The remaining, so the eigenvectors of C are in general called the principal components, are called the principal components. So if you want to reduce this data set to two dimensions, two principal components, you would use the largest eigenvalue and the second largest eigenvalue, right? And take those W1 and W2, those two eigenvectors, and project your data set onto those two vectors. Okay, and that will be your reduced data set. Okay, so in general, you will have lambda 1 greater than or equal to lambda d. Okay, and the corresponding w1 to wd are going to be called the d principal components. So if you want to represent a data set using only the top k principal components, what do you do? I'll just show you what you do for one data point. So you have xi, and you want to represent xi using k principal component. So far what you did, if you do it for only one principal component, how will you represent xi? On the line, right? So what will be the value?
So x1, x2 up to xt.
That is xi, correct? But if you want to represent it, so if you want to reduce the dimension and you want to express xi as the projection onto the line w1, what will it become? Okay, so see, if you want to represent a data point, I'll put it this way. Using only the first principal component, x1, xi will become what?
Xi transpose W into W.
The xi transpose w1 into w1. So this is assuming that you only have one principal component with you. But in general, you could have, let's say if there are two principal components, then what do you think xi will become?
Xi transpose W1 into W1 plus Xi transpose W2 into W2.
Exactly, right? So it will become, this is nothing but the projection. You are just projecting it onto a two-dimensional space now. See, this is a one.
Like we are doing summation here.
Yeah. So we are projecting it onto a line. For example, here we can't just stick with a line. So there is more information in other directions also. So you will go with something like this. Okay. So if in general, if you have k principal components, then xi will become w1 dot dot dot
Up
wk.
to xi transpose wk times wk.
Exactly, right? So that is what it will become. So in applications, what we will do is, see, this is, let's call this xi prime. What is, in which space is xi prime lying in? So what is the xi prime lives in what r what?
T minus 1 or D minus.
Think about it. So it's a linear combination of w1 to wk. W1 to wk are themselves in what space?
Real number.
D by
RD,
1.
I think.
Rd, right? So see, these are still in Rd. Okay, so you have not actually speaking reduced the dimensions as yet. Okay, so where is the dimensionality? Finally, if you want to throw away the dimensions, some dimensions, what you have to do is, so if you want to finally, so this is like the final point, right? So if you want to throw away the certain dimensions, you only retain the scalar projections along the first k directions. Meaning these k numbers, these will become your new coordinates. Okay, so I will now represent xi as this k dimensional vector, which is xi transpose w1. Okay, and okay, go all the way up to xi transpose wk. This is in what space? R?
RD.
R. So think about it. This is a
So
column.
RK.
This is an R, right? So there are, so what I'm doing.
Yeah.
So do you understand what is happening? So this is like finally the dimensionality reduction step, right? So what you have done is you have replaced. So there are two steps. So first, replace xi with its projection on the k PCs. Okay, so that is step one. So that will give you xi prime, this one. Okay, now all that is well and good, but then if you actually want the final reduced data set with only k dimensions for each data point, what you'll have to do is you'll have to retain only the scalar projections on the top k PCs. What do I mean by scalar projections? This is a scalar, right? So this is like you're leaving out the W1 part. You're only retaining the xi transpose W1, so on till xi transpose Wk. Okay, is this idea clear? So this is for applications, right? We won't ask this in the exam. So in the exam, it's enough if you understand to the extent of computing principal components, right? So if you know how to compute the first PC, if you know how to compute the second PC, that is that itself is a good task. So, but I hope you understand where the final reduction is coming from. Okay. Okay. So that
Can
is,
you explain the reduction part again, sir?
you are in R3, for example, right? So this is X1, X2, X3. They are all in R3.
R3. Yeah.
Now let's say you do PCA and you find out that this is the plane in which the data points are living, and the principal components are W1 and W2. Let's say this turns out to be W1 and this turns out to be W2, these two vectors. Okay. Now what is this data point's projection onto the plane? It is X transpose W1 W1 plus X transpose W2 W2, correct?
Yes, sir.
That is still in R3. Okay, so that is still in R3. So if you want only 2 dimensions to represent each point, what you have to do is for each point just retain this vector. So X transpose W1, X transpose W2. For each point, you will have to do this. You're only retaining the coordinates. If I want to I'll put it that way. So you're only retaining the coordinates corresponding to the projection.
So basically, we are only retaining the coordinates of xi on that plane.
Yeah, on that plane. Yeah, xi transpose W1. So this is like, so what is xi transpose W1 going to mean? It's going to
So the
correspond.
projection.
Yeah, the projection onto that W1 line. Okay, so for example, let's do this visually. Otherwise, it will be very hard. Let's take this example. No, I'll just assume that we have computed the principal components. Yes, this is the principal component. Okay, let's say the principal component first PC turned out to be this should not move. This should be okay. So this turned out to be the first principal component, meaning 1 by root 2 comma 1 by root 2, right? That vector. So W1 is 1 by root 2 comma a unit vector 1 by root 2, right? So this is the first principal component. So it is passing through this one. Okay. Now, what is the claim? The claim is that you don't need 2 coordinates. So you are going to approximate it with just 1 coordinate, right? So what will that 1 coordinate be? So what was this data set, by the way? This was the original data set. What was this original data set? 1, 1, 2, 3, -1, -1, and -2, -3, right? So instead of this, what we are saying is the dimensionality reduction, okay, or the data set after dimensionality reduction is XR, okay, for which I need only 1 value, okay, for all the 4 points. So this will be like a 1 cross 4 matrix. What is this value corresponding to 1, 1? What do I do? What do I add here? The projection of 1, 1 onto this line, 1 by onto 1 by root 2, 1 by root 2. What will that be?
Root 2, sir.
Yeah, so 2 by 2 by root 2, root 2, right? So I can now represent this point as root 2 in my new so like XR, right? So dimensionality reduced version coordinate of this is root 2. Likewise, I can do for 2, 3. So what will it be for 2, 3?
5 by root 2.
5 by root 2, right? So this will be 5 by root 2. Now this will be minus
minus 2 by
this will be minus 5 by
minus by root 2, yeah.
right. So roughly what is this saying? It's telling you that, you know, this is like root 2. You have to move root 2 distance along this line to find this blue point as the projection. You'll have to move 5 by root 2 along this direction to find the projection of this point, minus root 2 minus 5 by root 2, right? So you have, so in moving from x to xr, clearly I have lost information. Okay, but this is a trade-off that you have to live with. Okay, that's the whole point of PCA. See, PCA is not going to work always. See, that's the, after learning all this, you have to understand one thing, that PCA is not it's not guaranteed to work. So it may work, it may not work. Maybe at some other time we can discuss when it will not work. But if your data set really lives in a low dimensional, one dimensional subspace, okay, with a very small error here and there, then it's very good. So this will be a very good approximation of X, and you have managed to reduce one dimension.
So can't we say PCA is like inferring something?
Yeah, you are finding out patterns in the data, right? So that's what you are doing. You are inferring here. So the inference here is that,
Because it's not clarifying every time. We are giving answers, approximations, some. So
yeah, it won't give you it won't work every time.
actual answer, the exact value.
Yeah, that's true. See, first of all, you don't even know what the exact answer is, right? That's the problem, or that's the challenge with unsupervised learning. So there is no supervised learning. There is an exact answer. You have a label, but in unsupervised learning, you don't have a label. So okay, so there are two more things we have to do. I don't know if we'll have time. So there is a very nice geometric interpretation of PCA, which is effectively so you can interpret PCA as change of basis, right? So we will maybe discuss this some other time. Maybe I will stop with PCA as SVD, right? So this is the final point, and then we can close. So remember that. So what was step 1? Very quickly, just to summarize whatever we have learned so far. If someone asks you to find out the principal components, what will you do?
Covariance matrix.
Covariance matrix, right? So along the way, I'll also write down. So you have step 0, maybe is the data matrix, right? You have the data matrix, which is X, okay? This is D cross N. And then you will compute C equal to 1 by N XX transpose, right? And then what you are going to do is solve for eigenvalues, eigenvectors. So this is find and eigenvectors. Okay, so how is this tied to SVD? In SVD, if you're asked to find the SVD of these are the steps for PCA, right? This is PCA steps. Now, give me the steps for SVD. What will be step 1 if you want to find the SVD of A?
Find eigenvalues and eigenvectors
Eigenvalues is
Of what?
of the given matrix.
Okay. So A, but in this case, let's say it is X. So what will be step 1?
Find eigenvalues and eigenvectors of X.
Is it X? Because X is not.
X transpose.
Yeah, X need not be square, right? So the first step would be find either X transpose X or X. right? So that is what you would do in step 1 for SVD. Step 2 will be the same. So step 2 will be find the eigenvalues and eigenvectors of, let's say in this case, we do XX transpose. Okay, find the eigenvalues of XX transpose. That's what you will do, right? So do you now see the resemblance between SVD and PCA?
Yes, sir.
Okay, all that you are doing. So the only difference, main difference is between SVD and PCA is that in PCA, you scale the matrix X or XX transpose and then do the eigenvalue, eigenvector decomposition.
Decomposition.
Right? That is the only difference. In fact, if you do this, the eigenvectors won't change at all. So the eigenvectors of C and eigenvectors of XX transpose are the same. You can prove that. Only the eigenvalues will change. So in fact, the eigenvalues of the covariance matrix is very closely related to the dash of X. What could it be related to?
So variance.
So with relation to SVD, right? So eigenvalues of C is nothing but what? That's closely related to the eigenvalues of XX transpose, right? So eigenvalues of XX transpose are related to what values of X? So a square matrix will have eigenvalues, but a general matrix will have
Singular value.
singular values, right? So this is again something you have to see. So the eigenvalues of C are actually very closely related to the singular values of X. Okay, so that's a lot of content for one day. So you have to take some time and think about it. So otherwise it's not easy. This is not like very straightforward. But whenever you see that PCA is SVD, you have to think about whatever we discussed now. You can think of PCA as just an application of SVD. Okay, so I leave you with that thought. And yeah, if you have any questions, you can ask. If not, we will close. Any questions? Okay, yeah, so that is all I had. So today was a bit hard. I felt the kind of things that we covered, but so what you can do is, by the way, reference to the all that I covered today, maybe with a few exceptions, few things here and there. You can refer to Professor Arun Rajkumar's MLT lectures for week 1 and 2. Okay, and please go through this. You'll whatever we discussed is yesterday and today. It's all there in weeks 1 and 2. Week 1, not week 2. Week 1. Week 1, starting from the PCA part, because week 1 will also have introduction to machine learning, which you can skip. So, okay. So yeah, I'll upload the notes tomorrow sometime. We can meet again. So that this ends linear algebra, by the way. So next week onwards, for next 3 weeks, 8, 9, 10, it's optimization. 11, 12 is probability and statistics. All right. Yeah. So thanks for joining. See
Yes,
you.
sir. Thank you, sir.
Yeah.
Thank you, sir.
Thank you,
And
sir.
with this, we have covered all week 7 concepts, right?
Sorry.
I mean, with this session, we covered all week 7
Yeah, week
concepts.
7 is done.
Nothing is pending.
To my knowledge, nothing is pending, but I would say it is too vast so I'm not very happy with. So there are some gaps that I have left here and there. I would like to fill that with a little more rigorous proofs here and there, but for a first introduction to PCA, this is all we can do. Yeah, you can consider it as done. Theory-wise, it is done. On Saturday, it will be problem solving.
Okay, sure, sir.
Okay. Yeah, thank you.
Sir, is it fine to give 4 or 5 days of processing time for this PCA?
Yeah,
Like
yeah.
if I
Yeah, please do, because it is, there are like, in fact, there are many things we haven't even discussed. So we haven't discussed things like, so PCA is actually change of basis, right? So that I mentioned, we haven't discussed that. You can actually think of the whole principal component analysis as finding a different basis for the data set, okay, to represent the data set. That's something we haven't discussed. And
I have seen on NPTEL that way, like one of the professor, I think Mitesh Kapra sir. So he explained that way of changing. We plot these points on a different basis and look the variance how it is. And
yeah,
in
yeah.
that case, mean was not centered. I think. Or
Okay, okay. So yeah, we haven't discussed that also. Why is mean centering needed? Uh, there are quite a few things we have left out, but see, ideally, we don't need to discuss it in this much detail because it's not a course on machine learning, right? If it's a course on machine learning, then that level of detail is very important. But this is machine learning foundations, right? So PCA is actually brought in for only one reason, to show that whatever we learned about eigenvalues, eigenvectors, SVD, all that is useful. Okay, that's the, if you have to take away one thing, that is what you have to take away. So eigenvalues, eigenvectors are all useful somewhere. Okay, spectral decomposition, all this matters because it is used in some real world application like dimensionality reduction. So if you understand that, great. So you start with that and then you can slowly drill down and see other aspects of it.
yeah, because when I started watching lectures, I'm not getting anything like. So I just thought like, is it like normal or am I dumb?
No, no, it is very normal. So in fact, uh, when I tried to first understand PCA, so that was, I think, easily 10 years back. So at the time, I didn't know anything about PCA. So I actually didn't understand it at all because there are so many things that were missing. Finally, it clicked only after watching Professor Arun's lectures. So that is when I truly understood what PCA meant, and then even then it was not complete. Okay, so I had to spend some many days thinking over things, uh, trying to understand why one perspective is. So, for example, variance maximization, right? So, what exactly is the variance? Why is variance another term for information? So, these are all, each one is new information, right? So, you have to process that, and it can easily take 1 week to understand all that.
Okay, sir.
Okay, so for all concepts in this course, right, you will see this is one course, especially for those who are going to consider, say, writing something like GATE in your final year. The MLF is a very important course. Okay, so you'll have to keep revisiting the course. You simply cannot learn all of it in 1 year, sorry, in one term. Okay, so this one term, you have to, the strategy you have to adopt is learn as much as you can. You have to visit it again, maybe next year, year after that. Only then you will truly understand the whole content. Okay.
Yeah, so I actually have a question. Karthik, can you hear me?
Yeah.
So actually, I was going through PCA only, and I couldn't find it in Strang's book also, but it's basically over linear algebra, so I guess that it must not be present in it. But is there any good like resource for PCA also for like which can help me understand it much better? I get it a little bit, but I got that like notes from I guess I'm not getting it the like writer's name, some J something. But it is also good. But I wanted to ask you more about some other cool resource on PCA.
Okay. So there is a very popular primer on PCA. I remember reading it a very long time back. So it was written by, yeah, this one. So this is a primer on PCA by Lens. So this is like the example that I took about motion is also from this, right? So we have three
Okay.
cameras. So this is a very good document. So for example, but then see the problem with documents is the notation they follow, right? So see, for example, they have
Yeah.
yeah. So you have to, if you'll have to be comfortable with the see they
Yes,
are
like the resource that I was reading from, they mentioned decomposition, some different kind of decomposition method, JL decomposition or something like that.
okay.
It was not like we have studied till SVD only, and they had done decomposition through some JL decomposition or something like that, and
Right,
then it was based on, and then PCA was based on that only. So
right,
it was a little different, but that is a challenge. But yeah, still there. So the explaining methodology is quite nice. Like in PCA also, he used an example of four people who rated their food items, food choices, and based on that, they were able. He showed that the two types of vectors who are closely correlated and two types of vectors who are not closely correlated,
okay,
and the vector component, the component that is that is more impactful towards determining the dimension is V1 or V2 like that. So I have to go through it again also, but that is why I was hoping you could tell me. So I'll go through this also. Thanks.
yeah. You can take a look at this, and also Professor Arun's videos are kind of very good. So
Yeah, the one that are in our lectures, right?
yeah, on in MLT, yeah. So that is possibly the best that I have seen so far, and not just because it is there in our program, but because I myself
Okay.
understood it finally only after watching that. So
Okay.
okay,
Okay.
yeah. So see, if you understand SVD, so I would also put it this way. So if you understand SVD, then you have understood PCA. Okay, so the link between them is very strong. So there is a textbook
Mhm.
called Foundations of Data Science by Hoffman, Upcroft, Kannan, and so this textbook. Okay, this is freely available. So this discusses PCA, but then in the context of SVD. So if you go down to there is a section on best fit subspaces, singular value decomposition. So 40, right? So if you go to 40,
Mhm.
where is page 50? Yeah, so it starts here. So it starts with singular value decomposition, but then it will also explain the whole idea of projecting points onto a line. See, this is what we did today. So length of the projection, this is the variance, this is the term which contributes to
Mhm.
the variance, this is the term which
WI.
contributes to the reconstruction error. So minimizing this is same as maximizing this. So this is PCA, right? So but then if you notice, it's actually coming under SVD because they are the same,
Yes.
right? So they are the same. That's why these guys discuss very detailed discussion they do, and Pythagorean theorem, all that comes in. So singular vectors come in. You can actually look at the principal components as just singular vectors. So if you can read through this chapter, then this is very good. You could try.
The CS, the CS CMU EDU paper.
This is not the same as the CMU paper. So this is like a book. So this is Foundations of Data Science. You can say,
Foundations of Foundations of
yeah,
data science. Okay.
by
Sorry.
Hopcroft. Um,
John Hopcroft and Ravin Kanan.
yeah. These are some of the text resources that I have found to be useful. Apart from this, I am not aware of anything else because I haven't searched more than this. Maybe there are a few others out there.
Okay.
Okay.
Yeah. Thanks. Thank you.
So,
Yeah.
would you please pardon the name of the book? Actually, I have not written it down.
Foundations of Data Science by Bloom, Hopcroft, and Kannan.
Foundations of Data Science.
By Bloom, Hopcroft,
What?
BLUM,
BLUM.
Hopcroft,
Prof. Okay.
and Kannan. So actually, Professor
Thanks.
Watson actually uses this textbook. If you, I don't know if you are all aware of CMI. So Professor Madhavan used to maintain his website. If you go to CMI website, right? Yeah, go on. You were asking something. Let me see one second. So you might, if you can find his lectures, that will be great. So data mining and machine learning lectures. He has. So he has. This is his page. So how many of you know Professor Madhavan teaches data science also? We all know he teaches almost every single course that you can think of. So this is in CMI. So we all know he teaches almost every single course that you can think of. So this is in CMI. So he has supervised class notes, PCA class notes. PCA, does he have PCA? He has PCA. So this comes here. So yeah. See, he uses images to motivate. Nice images, yes. See, he has also done SVD only instead of PCA. Yes, he has like presented PCA as SVD. Okay, so
Yes.
internally he's following. If you go back to his written references anywhere, has he written references anywhere? He has not written references, but if I recall correctly, he follows this textbook only. So where is this references course outline? See, Foundations of Data Science by Bloom, Hopcroft, Kannan. So he follows this to some extent, I think, but not exactly entirely.
Yeah.
Okay, yeah. That all we can close. Can we close then?
So tomorrow will be another
Yes.
session on TA session, right? Tomorrow will be.
Sorry, tomorrow?
Tomorrow will be another MLF session, right? Or at 4, I guess, or 5.
Tomorrow for TA, there will be a TA session if I'm not wrong. So there is a TA session tomorrow, right? Tomorrow,
Yes, sir.
yeah. There's a TA session. On Saturday, there will be this problem solving session again.
Okay. Okay.
Okay, yeah.
So this today's session was impromptu session, or was it decided in yesterday's class? Uh,
Today, so I
because
had,
in my calendar it was showing for 5th only, but now today is 6th, I guess.
yeah, so we had decided, we had sent out one mail, right? That Wednesday and Thursday we'll have session from 9 to 10.
Okay. Okay. So
Yes.
I think I missed that mail. Sorry.
Yeah. Okay.